Hello, this is frq number 1 with 3 kg mass hanging from a solid cylinder, and then the solid cylinder has a mass. Right? Part A asks us to derive the moment of inertia for the cylinder to be 1/2 mr squared. Part A. So we know that for any object with a continuous mass distribution, the moment of inertia is equal to integral r squared dm. And since this is a solid cylinder, we know we would use rho and volume. So we know that rho is equal to m over v. And then we know that volume in this case is just area times your height. And the area of this would be pi r squared and then multiplied by L as your height. And then here we would just rearrange it where we isolate for m. So we have m r squared L times rho is equal to m. And then here we would take the derivative of both sides. So this would be 2 pi r L rho dr is equal to dm. And here we can go back to this equation we wrote in the beginning and replace dm with what we solved for. So I is equal to integral from 0 to r. These are your bounds because you go from the center to the edge of the cylinder. R squared times 2 pi r L rho and dr. And then here 2 pi L and rho are constants, so we can take them out and put it in front of the integral. So you have I is equal to 2 pi L rho. And then here, this r in the parentheses will combine with the r squared on the outside to become r cubed. R cubed dr. And then we would just integrate this. So it would be you go to 2 pi L rho, and then it would be r4 over 4 with the bounds from 0 to r. I'm going to plug in 0 and r. If you plug in 0, that'll just be 0, so we can just plug in r, so it'd be, or capital R, I should say, 2 pi L rho times r to the 4th over 4. And then here, we can replace rho with what we found earlier, which is m all over m r squared L. So I is equal to 2 pi L times m all over pi r squared L times r to the 4th 4. And this would simplify to be equal to 2 m r squared over 4, which will further simplify to 1/2 m r squared. Okay. Part B asks us to compute the magnitude of angular acceleration of the cylinder. Okay, so here we would use torque since the cylinder has a mass. So we know that net torque is equal to Fr, or F perpendicular to R. In this case, it would be the tension from the string. So it's equal to TR. But we also know that net torque is equal to moment of inertia alpha. And here I will set the two equations equal to each other. So TR is equal to I alpha. And then here I would just expand I into TR is equal to 1/2 m2 r squared alpha. And here I would denote that the 3 kg is m1 and the cylinder would be m2. And then here I would just isolate for t by just dividing r over, so we know that t is equal to 1/2 m2 r alpha. And then here I would use forces. So look at the net force on m1. Net force on m1 is just equal to m1 times acceleration. But then we also know that net force 1 is equal to fg1 minus t, which turns into F1 is equal to M1G minus T. And here I would just equal these two equations to each other so that M1A is equal to M1G minus T. And then earlier we isolated for T, so I'll just plug in T so that M1A is equal to M1G minus 1 half M2 alpha, or M2R alpha. And here I'll basically turn A, because we know that A is equal to R alpha, so I would replace A with R alpha. So M1 times alpha R, or R alpha is equal to M1G minus 1 half M2R alpha. And then I'll just move everything with alpha to one side. So M1R alpha plus 1 half M2R alpha equal to M1G. And then here I would factor out an alpha. So it'll be alpha times M1R plus 1 half M2R is equal to M1G. And then I would just isolate for alpha. So you know that alpha is equal to M1G all over that. M2R, and then I'll plug in the information that we know. So we know alpha is equal to 3 times 9.8 all over. And here I'll also factor out an R from the bottom because it's in both terms. So 0.3 times 3 plus 1 half times 30. And then plugging that into the calculator, we should get 5.44 rad per second squared. And it asks for magnitude, so we don't need the direction. Okay. Part C asks us to find the linear acceleration of M1. So we know that since it's attached with the string here, we know that, let me do that, but we know that it's like one system, so they have the same angular acceleration. And we know that A is equal to R alpha. So then we can just solve for A by just multiplying R and then alpha because we found alpha part B. And we know our R is 0.3. So A is equal to 0.3 times 5.44. So linear acceleration is equal to 1.633 meters per second squared. Okay. Part D. Part D asks us to find the number of revolutions made by the cylinder after 5 seconds. So we know that alpha is equal to 5.44 rad per second squared. And here I use displacement formula to find this displacement in rads, and then I'll convert it to revolutions. So we know that change in theta in rads is equal to 1 half alpha t squared plus omega I t, but then it starts from rest, so we can ignore omega I t. So we plug in our information, 5.44 times 5 squared. We get the displacement to be 68 rad. And to convert, we just divide it by 2 pi, so 68 rad times 1 over 2 pi. And this should be, and then you would get 10.822 revs. Okay. Part E, the scenario changes. So now there's a second mass, which I will denote as M3, which is hanging by the axle on the other side, and which causes an opposite direction torque. Okay. Part E Part E asks us to find the magnitude of the new angular acceleration of the cylinder. So just like in part B, I'll start off with net torque. But in this scenario, since there's two forces acting on it, which is the tension between the cylinder and M1, and then the tension between or the tension from the string from the axle and M3. So it's we know that net torque is equal to I alpha, but we also know that net torque is equal to T1R capital R minus T2 little r. And it's little r because it's attached to the axle, which has a different radius compared to the cylinder. Okay. And then we'll equal these two together, so we have alpha is equal to T1R minus T2R. Okay, and here I would go to net force, so net force on 1 is equal to M1A, but is also equal to mg1 minus T1. And just like in part B, it's basically the same process, and you'll be left off with T1 is equal to M1G minus M1A. And then here I would expand A to R theta. So T1 is equal to M1G minus M1 capital R alpha. And then for M3, we know that the net force is equal to M3A, but we also know that F3 is equal to T2 minus M3G. And then here it's T2 first because I'm making it where the 2 kg block will go up because of the motion. So here I'll equal the two equations I found. So T2 minus M3G is equal to M3A. And then here I'll just isolate for T2. So T2 is equal to M3A plus M3G. And here I'll do the same thing as I did for block 1. I'll turn A into R alpha. So T2 is equal to M3 lower R alpha plus M3G. And here I'll plug in T1 and T2 into the equation that we found earlier. So we know that, and I'll also expand I into 1/2 M2 big R squared alpha is equal to M1G minus M1 big R alpha times big R minus M3 plus or M3 lower R alpha plus M3G times lower R. And I just should be big R and R into parentheses. So we have 1/2 M2 big R squared alpha is equal to M1G big R minus M1 R big R squared alpha minus M3 lower R squared alpha minus M3G lower R. And here I'll just move everything of alpha to one side. So it would be 1/2 M squared R big R squared alpha plus M1 big R squared alpha plus M3 lower R squared alpha is equal to M1G big R minus M3G lower R. And here I'll just factor out alpha, so it'd be alpha times 1/2 M squared big R, or M2 big R squared plus M1 big R squared plus M3 lower R squared is equal to M1G big R minus M3G lower R. And I just isolate for alpha by dividing that big chunk, or the parentheses, to the other side. So alpha is equal to M1G big R minus M3G lower R all over 1/2 M2 big R squared plus M1 big R squared plus M3 lower R squared. And I just plug in its values. So we have, and at the top I'll factor out G because you have in both terms. So like 1/8 times 3 times 0.3 minus 2 times 0.03 all over 1/2 times 30 times 0.3 squared plus 3 times 0.3 squared plus 2 times 0.03 squared. And then we'll plug this into the calculator. Plus 3 times 3 squared plus 2 times 0.03 squared. And then you will get 5.075 rad per second squared. Okay. Part F. Part F asks to find magnitude of the new linear acceleration of m1, and we're basically using the same process as part C. So we know that a linear acceleration is equal to r alpha, but then in this case we are going to use big R because m1 is that distance away from the axis of rotation. So a is equal to 0.3 times our new angular acceleration, which is 5.075. So a is equal to 1.522 meters per second squared. Okay. G. Okay. G asks us to calculate the kinetic energy of the cylinder after m1 has fallen over a distance equal to 5r. So we know that its displacement is equal to 5r, and then if you could convert that, it would just equal to 5 rads. And here I would use common form to isolate for omega f. So we know that common form is omega f squared minus omega I squared is equal to 2 alpha times your displacement. And then here we're starting from S, so we can ignore omega I. So we know that omega f squared is equal to 2 alpha displacement times displacement. Okay, so the kinetic energy of the cylinder is equal to its rotational kinetic energy. So Ke of the cylinder is equal to 1/2 I omega squared, and omega in this case will be omega f. So Ke the cylinder is equal to 1/2 times its moment of inertia, 0.3 squared. And then we solve that omega f squared is 2 alpha times your displacement. So plugging that in, 2 times 5.075 times 5. And then you will get half times 30, 2.3 squared times 2 times 5.075 times 5. You will get 34.256 joules. Okay, part H. Part H asks us to determine the net work done on the system after 5 seconds. So the net work will just be the Ke rotational from the cylinder plus Ke from changing Ke for 1, and then the changing Ke for M3. So here we can expand all of them into work is equal to 1/2 times 1/2 times 30 times 0.3 squared times omega f squared plus 1/2 m1v1 squared plus 1/2 m3v3 squared. Okay, so we just need to find omega and then omega f, v1 and then v3. So we know that omega is equal to alpha times time, and we are given that we need to find it after 5 seconds. So do alpha times 5, you go to 25.375. So we know that omega f is 25.375, and then we know that v is equal to r omega. So then for v1 is equal to big R omega. And they all have the same omega because they're all like one system connected to like one cylinder. And the cylinder is like connected to like the axle. So is equal to 0.3 times 25.375, and that will equal to 7.6125. And then V2, same thing, but instead of big R, we're going to use little r. So R omega is equal to 0.03 times 25.375, which is equal to 0.76125. And just plug it in back into here. Work is equal to 1/2 times 30, 0.3 squared times 25.375 squared plus 1/2 times 3 times 7.6125 squared plus 1/2 times 2 times 0.76125 squared. And this will equal out to 522.13 joules. And that was FRQ number 1.